Hey everyone, my name is Kevin Bach from the University of Maryland. I just wanted to thank all the SIGCOMM organizers for making this event possible, and a big thank you to all the collaborators in this project. I like to say it's taken a village. Now today I'm going to be talking about censorship, and specifically a new form of censorship evasion we've been working on, server-side evasion. Now historically, censorship evasion to date has always involved the client. And this intuitively makes a lot of sense. If the client wants to evade censorship, it would make sense that the client would have to do something, whether that be configuring a proxy, installing software, modifying their packets, etc. This requirement has always posed a significant barrier to deployment. Installing software can often pose risks to the user, and beyond this, it can't help users who don't know they're being censored in the first place. Now, ideally, servers could help. Instead of deploying software at the client, we would instead deploy it at the server. And the server would subvert censorship on the user's behalf, without the clients needing to deploy, install, configure anything at all. Now this sounds crazy, but let's just think about the benefits. So this would immediately broaden accessibility and reachability. Many clients connect to one server. Clients don't need any technical expertise to download anything, configure anything. And it immediately uncensors all users who didn't know they were being censored in the first place. Now in this paper we show that server-side evasion is indeed possible. We successfully defeated censorship exclusively from the server for every country we tested: China, India, Iran, and Kazakhstan. And over every protocol we could get censored: DNS, FTP, HTTP, HTTPS, and SMTP. And in the process we get new insights into how censors work. We learn new things about the Great Firewall's resynchronization state, and posit new theories on how we think the Great Firewall is architected. Now in the paper, in the longer form version of this talk, we go into all these things in greater detail. But in this shorter talk, I'm going to focus specifically on how server-side evasion is possible, how we can do this from the server side. And then talk about a brand new result that has occurred since the paper was published, and actually since recording the longer form version of this talk. Us defeating a brand new form of censorship in China. So let's first talk about how server-side evasion is possible. Because if you think about it, server-side evasion, it shouldn't work. It shouldn't be possible. And to see why this is, consider the waterfall diagram of packets that are exchanged between client and server, leading up to the client sending a censored keyword. So the client starts us off with a SYN as usual, the server responds with a SYNAC, and then the client finishes the three-way handshake. And then the client sends the censored request. But the only thing the server does before the client is censored is it sends the SYNAC. That's it. And actually, after this packet is sent, it can't influence the connection at all. So due to the difficulty of finding ways to subvert censorship when all we have to work with is a single SYNAC, we used a tool that my team developed last year called Geneva. Geneva is a genetic algorithm. It's trained directly against live sensors, and it automatically discovers censorship evasion strategies by manipulating the packet stream, changing the packets in such a way that the connection between client and server is unimpacted, but that the sensor gets confused or is unable to properly censor the client. So we deployed Geneva across all of the countries and protocols in this paper, and amazingly, it discovered multiple ways to defeat censorship. So let's see what this can look like. So the first strategy I'll talk about here, this is one that works in China. There's a lot going on here, so I'll break this down. The client, as usual, starts off with a SYN, to which the server responds not with a SYNAC, but instead with two SYN packets. First, it sends a normal SYN, and the second SYN contains a payload. Now, this first SYN serves to trigger a TCP simultaneous open. This is an archaic feature of TCP that's actually still supported by every major platform, to handle the case in which two computers send a SYN packet to each other at the exact same time. When the client receives this first SYN packet, the client now sends a SYNAC. And it's actually this combination of a client sending a SYNAC immediately preceded by a SYN packet containing a payload that is sufficient to desynchronize the Great Firewall of China from our connection. And for the rest of this flow, the client and server can now communicate censorship-free. Now this seems crazy, but it actually works with varying degrees of success across all of the protocols we tested. And for context, the baseline success rate for censorship is around 2% in China if you do nothing at all. Now this is one successful strategy, but it's actually just one of many. And in the paper we detail 11 different attacks we found across these 4 countries. These exploit everything from not handling esoteric features in TCP correctly, error cases, confusing the sensor's logic, etc. And I want to note that none of these require any client modification. Many of these induce behavior from the client, but that induced behavior is whatever the default is for that TCP stack. There's no modification, there's no configuration changes, there's no software installed. And in the paper, we explore all of these and measure their success rates across all of the protocols we test, which actually led to a very strange result in China. What we were finding is that strategies work differently. They have different success rates depending on the protocol we apply them to. But this raises an interesting question because all of our server-side strategies operate strictly during the TCP three-way handshake. There's no data carrying packets yet, so there's no protocol yet. So why are different applications affected differently in China? And exploring this actually led us to come up with a new model of how we think the Great Firewall of China is architected. Because in the past, we've tacitly assumed that the Great Firewall works much in the same way the rest of our networking configuration works, with a nice sane separation between lower-level networking protocols and application layer protocols. But since we keep finding different TCP layer bugs for each protocol, what this must mean is that each protocol has its own TCP stack that we're finding bugs in. And what this strongly suggests is that the Great Firewall of China is running multiple censoring middle boxes in parallel. And this becomes more surprising when you think about how these censoring middle boxes are operating, because it is not the case that there's multiple censoring middle boxes, each listening to their own port. The HTTP machine is not just censoring port 80. You can make a request in China on port 80 with a forbidden, and you will get censored, or you can make a forbidden request on port 8000 or any port, and you will get censored. And this is true across all of these protocols. So what this suggests is that the Great Firewall is running multiple censoring middle boxes in parallel, all of which are independently tracking the state of every TCP connection entering and exiting the country, and then applying protocol filtering to determine, protocol fingerprinting to determine whether they can or should censor this connection. Now, since this paper was published, and since we've recorded the long-form version of this talk, we've actually seen China deploy another brand new middle box to censor something new, and that's encrypted SNI connections. Now, at the time we wrote this paper, the Great Firewall censored HTTPS connections by relying on the Server Name Indication field, or SNI. This is a plain text field in the TLS client hello, in which clients announce the name of the server they're trying to connect to. And censors have been using the SNI field to censor connections for years. ESNI, or encrypted SNI, is a new feature of TLS 1.3 that tries to address this by just encrypting the SNI field. Unfortunately, literally just days ago, China started blocking all TLS connections that use ESNI. And we found that the sensor behavior is actually a little different. It doesn't inject reset packets to sensor, it drops packets, and we found new residual censorship behavior. But we applied the tools and techniques from this paper, and in under 24 hours, we found 4 new server-side evasion strategies to defeat it. And I'd love to walk you through 2 of these now, since I think they really underscore some of the results and takeaways from our paper. So the first strategy I'm going to talk about, this is a new one. This is one that doesn't work against anything else. During the three-way handshake, the server simply injects a packet with the FIN and SYN flag set. And that's it. This packet alone is sufficient to desynchronize the Great Firewall from our connection. We hypothesize this works because the FIN packet during the handshake tricks the Great Firewall into resynchronizing immediately on this sequence number, which means it fails to increment its initial sequence number by 1 during the handshake. So this actually suggests this is an off by 1 bug in the Great Firewall of China. And this strategy doesn't work against any of the other protocols we tested in the paper. And this reinforces our conclusion from the paper that the Great Firewall is running multiple independent censoring middle boxes with their own TCP stacks. The second strategy I'm going to talk about, like many of the results from the paper, this works by inducing the client to perform a step that helps evade censorship. So during the three-way handshake, the server reduces the TCP window size to just 4 bytes long. And what this does, this induces the client to segment its request. So it sends a first packet with just those 4 bytes before our ACK packet restores the full TCP window. And this alone is enough to evade censorship, the CSNI censorship. Now this strategy shouldn't work. The Great Firewall can reassemble TCP segments, and actually as a client, if you segment your request at any byte index greater than 4, the strategy stops working. We hypothesize this strategy works by defeating the protocol fingerprinter within the Great Firewall of China. Since the TLS header is 5 bytes long, by segmenting our request at less than that, we're preventing the Great Firewall from identifying this request as something it can censor in the first place. So even though the client had no special software deployed, the server could coax it into this anti-censorship technique just by reducing the window size. And these are just two of the strategies we discovered against the new ESNI censorship in China. So to conclude, we've shown in this paper that server-side evasion is indeed possible. In the paper, we present 11 strategies in 4 countries across 5 censored protocols and glean new insights into how sensors work and how they're architected. More details are available in our paper, and our code and updated results are all available at our website. Thank you.
Thank you. That was wonderful. So we have a few questions on both Slack and a question on Zoom. A lot of them have a common theme, which is now that you have this tool, how easy is it for the censor agency or the people who do the censoring to kind of figure out, sort of to kind of beat your scheme, so to speak, right? So Gargi Mitra has that question. So does Kevin Glane. And Shayoki from Princeton asks, what prevents the censor from running Geneva themselves and kind of figuring out some issues and bringing them in?
Yeah, it's a great question. And it's a question we get pretty frequently with work like this. The short answer is nothing. There's really nothing preventing them from taking these tools and techniques and testing them themselves. Much like nothing's been stopping them in the past from trying Tor out themselves to see if it defeats their censorship systems. So there's really no magic to what we're doing. Like the censors could have been doing fuzz testing on their own systems for years. We've just made it more accessible for the rest of us to do it. What I'm hopeful is going to happen is Geneva tends to find 2 classes of bugs, 2 classes of strategies that work. The first is these implementation bugs, things that we think are easier for the sensors to patch, something that's a relatively one-off or strange singular result. The second class, though, is a more systemic problem in how the sensors are architected in the first place. For example, how they track state in and out of the country. We think those are significantly more expensive to fix. So to answer the question, there's nothing stopping them from using the tool, but we're hopeful that the issues we expose are sufficiently expensive, either computationally or financially, to fix, that they'll work for longer. And automating this makes it democratizes the ability to find this. So just like the authoritative regimes could identify this, evaders can too.
Got it. I think you also answered another question that came up as to would this approach raise the cost of censorship, or are any of these difficult to adapt? That was asked by Brighton. I think you've sort of covered that in this response. There's a question from Ethan from Columbia, and he says, since some of the techniques rely on infrequently used features, do any of them rely on variations in client-side implementations? So do they work for some implementations but not others?
Excellent question. The answer is yes. There were 3 strategies we found in the paper that relied on features specific to Linux. That being said, we were able to modify them, very minor modifications, such they were supported by all major operating systems. And in the paper and the longer form version of the talk, we speak to the various operating systems from the client that we test these on. I think we tested across 14 or 15 different operating systems and versions, Windows, phones, etc. So everything in the paper is very broadly supported, but it is technically possible to find strategies that are specific to a single OS if you don't do that broad testing.
Okay.
I would just mention real quick, there are middle boxes though that could block some of the strategies because of their own way of keeping state.
Thank you. A question from Inan Zai. What is the exact adversary model for your work? What behavior assumptions do you make for the censorship?
It's a good question. I think it depends on the censor. In the paper, we have 4 different countries we study specifically, and within those countries, we study multiple protocols. And the models can kind of change country to country. So this might be an easier question to take offline or answer in Slack, or just consult the paper. Yeah, I think that's a better question to take offline.
Yeah. So, you should probably discuss this more on Slack. I had a non-technical question. So when you do it on the server side, do you open the room for new sorts of, say, political issues? So is it possible that, say, China could put political pressure on, say, Google when they try to deploy these techniques and say, you'd lose these other perks?
Very potentially. We're going to have to see how the world shakes out as these things, as people start looking into deploying these things. That's definitely something we've thought about, but really TBD what that's going to look like in the future. It's a great thought, though.
Okay. A question from Anya Feldman. She starts off by saying it's neat work. And could your techniques trigger IDS systems that are looking for weird TCP behavior? Example, bro.
Another good question. In practice, possibly. It really depends on what bro is looking for. In theory, you could train Geneva against both a firewall and with bro listening to try and defeat both, or just to defeat bro, or encode in the fitness function of Geneva to make it such that the packets it finds do not look too anomalous. We didn't do that in this paper, just as a first pass. We really wanted to prove that it was possible in the first place. Like Louis Henry mentioned, it is possible that the strategy we find will fight or collide with other middle boxes, and bro is just one example of something like that. So TBD, we'll see.
Hi, that was an interesting talk. While we wait for questions, so now that the great firewall operators have also seen your paper, how many of these like evasion strategies can they kind of easily stop, and which of them are kind of hard to beat?
That's a great question. The short answer is we're not sure. We can reason about these, and we reason about this a little bit in the paper. Geneva generally finds two classes of strategies. There's smaller bugs that we think are easier to patch. We think those will be patched more quickly. We also find more systemic issues in how these things are designed. We're hopeful that those are more expensive, costly, or time-consuming to patch. So the answer is we're not sure. We're monitoring it, and time will tell.
Okay. And what about UDP and quick connections? Do you have you looked at those as well?
So we didn't look at quick specifically for this paper. At the time of writing, we couldn't actually observe any censorship over quick at the time.
Okay.
The only UDP we examine is with DNS. There's no server side UDP strategies because there's no handshake. By the time the packet gets there, it's too late. So we focus on TCP for this paper.
Cool. And do you have any insights on how you can kind of design new, like if you have any tips for kind of changing the TCP handshake to be more kind of evasion friendly?
Ooh, that's a tricky one. I'm not sure. That's a tough one. I've never been asked that before. Louis Henry, what are your thoughts?
I'm not sure. I mean,
yeah, this is a bit open-ended and yeah.
I feel like a nice property that we have with TCP right now is just there's relatively consistent behavior across many systems. We show in the paper we train these strategies against specific operating systems, but we were pleased to find they were pretty broadly applicable. So a nice feature of TCP actually is that it's relatively standard. With almost no modifications, we were able to get all of these strategies working across basically every major operating system, phone, mobile, desktop server that we were able to test. So that'd probably be the answer I'd buzz in with.
Yeah, cool. There's a question on Slack. Have you considered not publishing these strategies?
We have considered it. We have worked with other groups that we give these strategies to such that they can use it. It's an arms race back and forth, and there's definitely some cost benefit analysis to publishing these things. Getting to talk with you people about it is one of those benefits, and sharing the work more broadly. So we're hopeful that the benefit of sharing this with you all and spurring additional research in this area and getting additional eyes on it is worth the potential cost of great firewall operators seeing it.
Mm-hmm. There's another question out of curiosity. What was the insight that led you to arrive at a genetic algorithm?
Great question. So we had actually developed Geneva in the past, and we had published a separate paper on how we designed and implemented Geneva itself. So the insight specifically was a blend of we wanted a learning algorithm with a high degree of explainability. We wanted to be able to know what it was thinking and get a good insight of how it was working. And it was relatively easy to once we had a good idea of how we could encode and create censorship evasion strategies in the first place, a genetic algorithm was just a natural progression to that. Evolution was a good way to evolve those.